This video presents the information on recording runtime statistics for benchmarking. A key aspect of optimizing programs is to, of course, measure its runtime statistics so that we can compare and contrast the performance before and after optimization. The common statistics that are typically used for comparing programs would be the runtime, the number of CPU cores used, and sometimes the memory used as well. Linux provides a convenient utility to record and report runtime statistics, which is user bin time. And when we work with user bin time, we will typically discard the program outputs, particularly if the outputs are large, so that we can focus on timing data that user bin time prints, and of course minimize some of the variances in the timing that can arise from input-output operations. User bin time prints information in two different formats. It can either be a succinct format or you can have a verbose format where all of the details are printed out with a more verbose description of each one of the statistics. So initially when we get started, it might be handy to have the verbose flag set so that we can get detailed output so it's easier to remember and work with it. Let's look at some of the key statistics that we will record with user bin time. The first one is user time. The user time is the total amount of CPU time that's taken to run all of the instructions in user mode. Yeah, this is the time that is spent, or the CPU time that is spent in running instructions in user space instead of kernel space. And also keep in mind, this user time is a sum of the CPU time of all the cores that is assigned to that job, or depending on the number of threads. So it's not just one core or one thread, but it's the sum of all of the threads. And typically, this value will only mildly change for a deterministic program. That means you're processing a deterministic algorithm, you're giving deterministic input. The net number of instructions that are run by the program should remain about the same, and consequently, the user time will remain about the same. The system time is similar to user time, but it's the time taken to run instructions for syscalls from the program. And remember, syscalls are calls to the operating system to perform various input-output operations, memory management, thread management, so on and so forth. So again, this depends on, for a deterministic program that's processing a fixed input or a given input, this value is only very mildly influenced. That means it will remain almost consistent from run to run. The next statistic that we'll typically look at is elapsed time. This is the runtime of the program as observed by the user. So if the user hits a stopwatch when they start running the program and hit the stopwatch when they stop, that time between start and stop is called elapsed time. This is also called wall clock time. This is what the stopwatch or a wall clock time would be. And this value is heavily influenced by other running processes due to multiprocessing, context switching. So if on a heavily loaded machine, to get the same amount of user time, the operating system may have to context switch a lot of processes, so the elapsed time for the program might increase. So on lightly loaded machines, that means the program that you're trying to benchmark is the one that is heavily using the CPU. This value will be somewhat repeatable, but there will be some level of variance or noise in this data because of context switching and other background operations happening in the operating system. Another common metric that we'll use, particularly for multi-threaded programs, is the percentage CPU used. So this is the average number of cores that were utilized by the program while it was running. In Linux, each core is accounted at 100%. So if a program on an average uses 3 cores all the time, you will see a CPU usage of 300% coming up for that specific program. For example, in this example, there is 195%. That means on an average, this program was using about 2 cores. So 2 cores would have been 200, but 195 says it's pretty close to 2 cores. So these are the key statistics in terms of elapsed time, user time, system time, and percentage CPU that we would typically record for benchmarking and comparing the performance of programs before and after optimizations. Sometimes we'll also look at the maximum residence size, which is the peak amount of memory that is used by the processes. This is usually reported in kilobytes by user bin time. And in general, on very lightly loaded machines, that means no other program is really using the CPU, your elapsed time will be the sum of user time plus system time divided by the percentage CPU. So on lightly loaded, this relationship will roughly hold. Now let's understand the statistical sensitivities of performance comparisons and the need to use compute jobs on clusters for benchmarking. User time is used to collect runtime characteristics of and to compare performance of programs. Keep in mind, when we compare performance, statistics from independent and identical runs must be sampled and averaged. And this average is important because there will always be noise due to system tasks, such as due to preemptive multitasking or networking or input-output operations that might be happening on the system at that time. Typically, when we do this, we should try and dedicate CPU cores to the process that we are benchmarking, and this is to minimize variance so that we can collect statistically reliable and repeatable data. And this is important for short benchmarks or microbenchmarks in particular. Keep in mind, minimizing the variance, when we reduce this variance, what we are really trying to do is reduce the number of samples that are needed for statistically significant comparisons. And to reduce this variance and reduce the noise, for benchmarking, we'll use compute jobs so that we reserve CPU cores for the process to reduce the variance in runtimes. From a statistical perspective, the number of samples we'll need to collect will depend on the nature of the variance in the data set. So based on the variance in the runtime, and of course, what is the acceptable error margin that we are willing to deal with in the statistical analysis. So for example, typically we look for a 95% confidence interval. So for this, if you look at the tables for z's of alpha, for a 95% confidence interval, we'll get 1.96 for z. And given that value, let us assume that we have an acceptable error margin of about 2 seconds. That means maximum error that we might have in comparisons is going to be plus or minus 2 seconds. So that means the variance in the data needs to be small. That means we need to have less than 2 seconds of variance. And to get this level of tight variance will require a lightly loaded or a dedicated machine. And typically we'll accomplish this via a job on the supercomputing cluster. So assuming that we are able to reduce the variance, this is the assumption. That means we are assuming our variance is acceptably small. Then if we just have 5 samples, that will be sufficient to make a statistically significant comparison. So notice all of this. That means assuming this is the error margin, assuming we're able to keep the variance small, 5 samples are sufficient. However, in practice, if these assumptions don't hold, then you'll have to go back and use statistics to understand and calculate the number of samples you'll need to make statistically significant comparisons. When you're running a benchmark on a cluster, the typical steps that will involve will be to compile the program using suitable optimizations flag. Typically, we'll use -03. For short benchmarks, we will use interactive jobs on the cluster just to ease the process of benchmarking. So to start an interactive job, you'll use the sinteractive command, and then you will specify the number of compute nodes you will need. Typically, we'll just use 1 compute node for now. And then you'll also specify the number of cores to reserve on each compute node. Typically, we'll reserve 4 to 8 cores for some of the benchmarking work that we will do. And later on, when we are benchmarking MPI or distributed computing programs, the number of nodes that we will use will increase. And then once the job starts, you can run your program with user bin time to record the statistics. And then you record the statistics several times to get the data for averaging and comparing runtime data. Let's understand how the jobs work on the cluster. Typically, when you start working on a cluster, either you'll be on a login node or you might be running on a compute node as part of your VS Code jobs. So keep in mind, when you start a VS Code job, the current job may have a different set of resources. So typically VS Code jobs will run with just 1 CPU core. So running multi-threaded benchmarks or other programs will compete with the VS Code processes that are running. So you may not get a you will have a lot of noise in it and you will not get a statistically significant result. So the key here is whether it be in a VS Code job or in a regular terminal, your job might be running on a compute node. So let's say in this case, let us assume it's running on compute node P0110. When you start a job, first the job management system will tell you that it is looking for a job. In this case, what it's doing is it is searching through the cluster, looking for a compute node that has a free resource. Once it finds a compute node that has a free resource, it will move the current shell to the compute node, and you will see that it will drop you off onto a different node for you to run your job. Here you can run your user bin time commands and do your performance testing, collect all of the data. And since you're now running on a dedicated node with dedicated CPU cores, your timings will have less variance and provide a much better statistical samples that will be independent and identically distributed for statistically sound comparisons. And once all the tests are done, you'll typically exit out. And when you exit out, you'll come back to your regular VS Code terminal and you can do other analysis that you need to do. Now let's take a look at how this looks from a VS Code terminal. I already have a simple microbenchmark set up here. Basically, it's using the sort method to assess how the sort method performs under different multi-threaded conditions. Here we are using the built-in GNU parallel libraries to multi-thread sort. So note that there's no explicit multi-thread, like there's explicitly you don't see the threads in the source, but that explicit threading is happening behind the scenes for you as part of the GNU parallel library. And also notice that here I'm on the current host name that I'm on is some 840, so I'm on a different host name. Let's try and see what happens when we run this benchmark on this node without creating a job. So here I'm just going to run with 4 threads. I'm going to run this benchmark on this current compute node. I'm also going to make my terminal larger so that you guys can actually see the statistics a little bit better. Yeah. So this benchmark is running, and notice that even though I was hoping to be able to use 4 threads on 4 cores, this job only got like 84% of the CPU. That means it did not even get a whole core to run with. Why is this? This is because in this default shell, remember when you look at the code server jobs, they are all running on one node, one core. So at the most, the job and the shell can use only one core. And this job is already competing with the VS Code background processes, so it's not getting much core usage here. Yeah, and that's why the elapsed time, notice that the elapsed time is 12 seconds, but the user time is only 10 seconds. That means to get the 10 seconds of compute, I actually had to spend 12 seconds of time. Yeah, so that means there is more context switching or more background work that is happening. In this case, I didn't also redirect the output to /dev/null because this is just a short output, so I didn't redirect it to /dev/null. Now let's contrast this by running running this benchmark from an interactive job on the cluster. Here I'm going to start an interactive job looking for 8 cores, and notice that this allocation happened pretty fast, and now I'm on a different compute node, P0160, which is a different node than before. And then it'll automatically drop you into the same folder that you are. So I'm going to rerun that benchmark again now with 4 cores. I'm going to run that. And previously it took about 10 user seconds. Here it took a little bit higher because it was creating threads and all of that stuff. And notice that now we were able to, the elapsed time substantially reduced because the percentage CPU that we got for this job increased. Because we had 4 cores, the job was able to use almost 3 cores most of the time to complete 11 seconds worth of compute in just 4 seconds because of multi-threading. And this is how you will run the same command multiple times on your job, and every time you run it, your typically your user time will be almost the same, pretty close. We are generating random numbers, so there might be a little difference there, and your elapsed or wall clock time should be pretty close as well because we have reserved the compute node, so we will not have much interruption here. Once you have completed all of your benchmarking, you'll exit out of the job, and you'll see that it'll put you back into the original host that you started from. Remember, the jobs were running on a different host, And then when we exited, we came to a different host. And this kind of demonstrates how you'll use a VS Code terminal for running performance benchmarks on the supercomputing cluster. That completed this presentation. Hope you learned how to do some basics of benchmarking. Good luck with your benchmarking experience on the supercomputing cluster.